So I understand you've been talking about the Archimedean property of the real numbers. And he has, I think, a proof to do about that still. So I won't do the proof, I'll just state the property, and we'll use it to do some problems about intersections and unions of infinite collections of sets. Do you guys have any questions before we get started? Yeah?
Can you just quickly state what an open set is versus a closed set?
An open set?
Yeah.
Yeah, so I think you're talking about open sets in the real numbers.
Yes.
Right. So I'm not sure what definition you have, but I like to think of an open set is it's a union of open intervals. It's just some union of some maybe infinite collection of open intervals. Does that sound like a definition you had?
I think ours
Because
is defined as it can be expressed as an x plus r and x minus r. Actually, call it.
So that, yeah, so to be an open set, every element in the set has to have an interval around it that's still contained in the set. So that's your x plus r and x minus r. Okay?
Set R
Yeah.
is open if and only if for all x in the set there exists some r greater than 0.
Yes.
Such that the interval is between x minus r and x plus r. And then closed
Yes.
is if it's a complement of that.
For each x in the set, what do we have to say? There is an r. Is it a small r or something?
Oh yeah, technically it's small r.
Okay.
Greater than 0.
Yeah.
Such that the set is between x minus r and x plus r.
Yeah, so that x minus r, x plus r is contained in your set, right?
Yep. And then closed is the complement of that.
Close is the complement, right? So yeah, I guess that's the best way to think of a closed set.
Okay.
Check and see if the complement of the set is open. It doesn't mean that a set has to be either open or closed. Okay. Standard example of an open set is an open interval. Okay, so if we have, let's say the interval from 1 to 3, that's an open interval. Okay. Every element in there has a interval around it that's still in this interval from 1 to 3.
Oh, okay.
Okay? All right? But it could be that it's, it's put together out of several pieces. Maybe it's also going to have the interval from 5 to 6. Okay, so the union of those is still an open set. So I don't know how much you've talked about, but the union of open sets is also an open set. And okay. But there are some kind of unusual examples too. Other questions?
Can you just visually, very quickly do a closed set? Just so you can do
A closed set? Yeah.
So
So a closed set, so a closed, so let's just say a set, can I call it C in R is closed if the complement, we can think about what this means, but the complement S, which I think you write a bar for the complement, is open, and then we have to think about what that is. So like, but a good example is a closed interval, all right? Let's check. So again, let's take an interval, but now we're taking a closed interval. So we're including the endpoints. Okay. What's the complement? So my set S is the complement, so 2 is not included, but everything less than 2 is included. 6 is not included, but everything greater than 6 is included, right? So we just removed that. Okay. This is an open set, right? So any point that I pick, I can find an interval around it that's still in my set. It happens to be infinite, but that's okay. All right. So this is open. So this is closed. Notice that this is not open. The problem is, if I pick this point in my set C, I can't make an interval around it that's still contained in my set C. I had to go to the left of 2, and then I've gone outside. Okay.
So is something not open and not closed if it's like piecewise, so it has both?
Yeah, it could be that it's like an interval that's open on one end and closed on the other. So then that's not going to be open and it's not going to be closed. Okay? Got it? So, they're much more complicated examples, but that's just the idea of the definition. Okay. Anything else you want to ask? Okay. So let me put down the Archimedean property. Of the real numbers. It's actually involves the real numbers and the natural numbers. So it says if you have any positive real number, there is a positive integer so that we have this fraction will be less than the x. Okay? So here we're talking about real numbers. We know they can get arbitrarily small, and this is sort of saying, well, fractions made with natural numbers can actually become arbitrarily small as well. Okay? But this is something that we have to prove. It's proved from your least upper bound property, right? I think you talked about that. So the idea is we can't prove everything. We have to start from somewhere. Certain things that we accept without proof that we call axioms, right? And so this was one of the things you were going to accept as an axiom without proof, but this is proved from that. I'm going to let Professor Dupuis finish doing that when he comes back. So we'll just assume that we know that fact. Okay? All right. So what we're going to do is use this to prove some things about intersections and unions of sets. And the idea is all of this just translates into facts that we know from logic about quantifiers and negation and making logical arguments. Okay, so here's an example. So we're going to talk about infinite unions and intersections. Okay, so I'm just doing these problems that Professor Dupuis suggested. All right. So what does this mean, first of all? You pick a natural number, start with 1, and you substitute that in, you have this interval. Okay, so we're talking about intervals and the real numbers here. And you could pick 2, and then you'd have the interval from 0 to 1/2. You could pick the interval from 0 to 1/3 when your I is 3. But I can't write infinitely many things. And so this is kind of a nice, handy notation for that. So it's an intersection of infinitely many things. And officially, what does it mean to say that something is in here? To be in the intersection means to be in every one. Okay? And that's something we can say whether there's a infinite collection here or a finite collection. If it's in this intersection, if it's in every one of these, and vice versa. If and only if it's in every one of these. Okay. So by the way, sometimes I might like to use a different letter. Does it matter if I write n instead of I? It's the same thing, right? We're still going to be substituting n equals 1, 2, 3. You might call it a dummy variable, like in calculus. Your variable of integration disappears when you do the integral. So yeah, so if we want to use I instead of n, you can. I think I might use n because it's going to match this a little better. Okay. So what we want to prove, our claim is we want to prove that this is actually the empty set. Okay. All right. So how should we prove it's the empty set? I mean, you can kind of see why, I think, right? So if it's in here, it's less than 1. If it's in here, it's less than 1/2. It also has to be less than 1/3. And to be in each one of these, it has to be less than 1 over n. So it seems like there's nothing left. Well, okay, we want to prove it officially. Okay. Suppose I have an x that's in here. Let's see what we can say about it. We're just going to use our definitions, right? So this means that x is in every one of these. That's what the intersection means. For all of these. Good? And what's the reason for that? It's good to explain. That's the actual definition of intersection. Okay. First thing, is the x greater than 0? Yeah, in order to be in one of these, it has to be between 0 and 1 over n, so it has to be greater than 0. Okay, so that's the first thing we know. Let's just be specific. I could just say when n is 1. The x is greater than 0. It also has to be less than 1. Okay. I just wanted to do this because I'm going to try to use the Archimedean property here. So that worked out. Okay, and we're talking about a real number. Great. So now we can use the Archimedean property. Oh, so sometimes we'll write it with a small a. I don't know if you usually use a capital A or a small a. But I had a professor once who said the greatest honor for a mathematician is if we get to the point of writing their name with a small letter. So Archimedean is in that category. So the Archimedean property says, all right, there is an n, okay, which is a natural number. With the 1 over n less than x. Okay. And here, I just might like to kind of emphasize this is a single n. So maybe call it n0 or n naught. So that's one n there, whereas I think of this n as being a variable, right? I choose lots of different values of that n, but this is just one. Okay. So far, so good? All right. So is x in the interval from 0 to 1 over n0? Based on this? No, right? It's not. It's greater than that. Okay, this would say that x is less than that. Okay, great. So what did we find? We found that there is one of these intervals that the x is not in. So could x be in the intersection? Nope, right? Hence, we have to think about our quantifiers, right? So this means that x is in every one of these. We just have to find one that is not in, okay, to show that it's not in the intersection. Okay. X in here would say it's in every one of these. Everyone okay with the quantifiers? To show that it's not in every one of them, we just have to show a single one that is not in. Okay? All right, this is sort of a problem. We started by assuming that x was in there, and we concluded that it was not in there. Okay, so we get a contradiction, you could say, to our original hypothesis. So what do we have to conclude? There can't be an x in here at all, right? There's no x in there. That the intersection has nothing in it. Okay. Good. So that's my proof of my claim. Good. So I referred to what I used. I referred to the Archimedean property. I referred to the definition, maybe I should say, by the definition of intersection here. Okay. All right, that was a relatively easy one. What about an infinite union then? I don't think we'll use the Archimedean property for this. Okay. So let's do an infinite union. This one, we're still doing one set for each natural number, but this time it's not an interval, it's just a set of two numbers. Okay? So just to be clear, right, just to get the idea, the first set has 1 and 2, the second set has 2 and 3, the third set has 3 and 4. Okay. What do you think the union of those is? It's going to be all the natural numbers. We've got 1, 2, 3, all of them are in there. using the definition of union. So what does union mean? We can't say it's the union of this and this and this infinitely many times. We say an element is in the union if and only if it's in one of these sets. If there exists one of these sets that it's in, right? Okay, so that's our definition that we'll use. So we claim, our claim is that this is going to be all natural numbers. Okay, so our proof generally has two parts. Two parts would be, first, that right, that this set is contained in that one. Second, that this set is contained in that one. Sometimes you can do both steps at the same time, but it's often simpler to do them one at a time and to be sure that you've covered every possibility. Okay? So that's what it means for two sets to be equal. They have the same elements. The elements in here are in there, and the elements in here are in there. Okay, so oh, by the way, why didn't I have to do two parts over here? I wanted to show these two sets are equal. Basically, so the other part would be to show that this one is contained in there, right? Is there really anything to show? No. To show that the empty set is contained in here? No, the empty set is contained in everything. All right. Just to point out that, yes, there should be two parts in general, and showing that two sets are equal. Okay, so showing two sets are equal, first, break it down into two different subsets, and second, use the meaning of subset in terms of elements, right? So how do I show this? What do you think? Where do I start? Yeah?
Since n's, any natural number in it is in the set, doesn't that mean, so it will always be that first element?
So, yeah, so we start by talking about elements, right? So that's what the point I want you to remember is that start with an element, right? Don't think about the set all as a whole. Think about a single element, but arbitrary element in there. So for one, if we have an element in here to start with, let's call it m. I'll use a different letter since I've already got n's over here. We need to show that m is in this second set. Okay? Subset means every element in here is in there. Take an element in here, show it's in there, without specifying any particular element. Okay, so this means that it has to be in one of these. Which one do you think it's in? So for instance, if I picked 6, which of these is it in? Well, one of these has 6 and 7, right? Or there's another one that has 5 and 6. I could pick either one of those. Okay. So, so given this in here, then my m is certainly, let's use this one. Okay. It's in that set of two things, right? Okay. So there exists an n, namely, maybe I'll call it n naught, namely this m with m in this set. And that's exactly what it means to say that M is in the union of these. It means there exists one of these that has M in it. Okay? Good. So we did show this, starting from this. Okay? So that part is done. Then we do the other direction. Part 2. This time we're given an element in the union there. Okay, again, we're going to use what's the meaning of the union? Well, it's in one of those sets. There exists one of these that it's in. So there exists one of these. That M is in. Right? Okay. Well, so then there's only two things it could be. Right? And we said this was in the natural numbers. How about this? Is that a natural number? Yeah. I think you talked about this kind of formally, that if you add 1 to a natural number, you always get a natural number, right? Okay. So in either case, in any case, the M was one of these numbers that's in here. All right, and that's what we wanted, right? If it was in here, we showed that it was in here. And we can say then, since the M was an arbitrary element of this, every element in here has to be an element in this set, right? Okay. Maybe to finish off the proof, M in here we conclude that this whole set is contained in this whole set. Okay. And that's our second one that we wanted to prove. Okay. Simple enough? Okay. What do you think is the intersection of these? Yeah. So if I took the intersection, I would say, what belongs to all of these sets? Okay, so to say that something is in the intersection means that it's in all of them. It would have to be in these three. What element is in all three of these? Nothing. 2 is in the intersection of these first pair, but then it's not in here, so this intersection is empty. Okay. Okay, so again, we could prove that formally. That X, or let's call it M, if it's in the intersection of all of these. Okay. I mean, we could do it by just what we said there. M is in here for all n, the positive integers. In particular, it has to be in well, let's even just do the first one and the third one, right? Okay. It's in every one of these, so it's in this one, it's in this one, and everything else too. But already, there's no such m, right? Okay. So there can't be anything in here, it's the empty set. All right, so that was kind of warm up for a little more complicated example where we're going to have to do some scratch work. Okay. And one complication in this problem is that we're going to allow all real numbers, okay, that are greater than 0. I think I'm going to say greater than 1. Okay. So this will be quite different if I'm allowing x to be any real number greater than 1. So I can pick x equals 1, and I get the interval from 1 to 1 squared plus 1. I can pick the interval, I can pick x equals 2, and I get 2 squared, 4, and then 4 plus 1. And I can pick x equals 3, and I get 9 to 10. Okay. And maybe it looks like I'm leaving out numbers between 2 and 3. But it's important to realize this says x can be any real number. So I could pick x equals 1.2. And then I would have, let's see, 1.2 squared, 1.44, and add 1 to that, 2.44, right? So in fact, I do get intervals greater than 2. I get numbers greater than 2 when I take this union. So what do you think I'm going to get here? I'm going to get all of the real numbers greater than 1. So that's what we want to actually prove, is that there aren't really any gaps if you're allowed to choose all possible real numbers within an interval. Okay, so this is a little bit different. Okay, so that's our claim that we want to, not all real numbers, only greater than 1. So from 1 to infinity, though. All right, so that will be our claim. All right. Same thing. We're going to have 2 parts to show that this union is contained in here, and then the other way around. Okay. We usually do the easy one first, and this is probably the easy one. Okay. So again, what do? We say pick an element in here, show that it's in there. Okay. Okay. Well, if it's in the union, it means there exists one that it's in. If you want to emphasize that there's a specific x that we end up in, then I'll call it x naught. Okay? So let's see. the x naught was, oops, I wanted it to be greater than 1, right? Okay. I'm just going to stick with x's that are greater than 1 here. So is the a greater than 1? Okay, if it's in this interval, it's got to be greater than this, less than that. And I'm saying that the x's that I pick are always going to be greater than 1, right? So this will be greater than 1 squared. Actually, this is a strict inequality since I have an open interval there. Okay. Okay, so my a is strictly greater than 1, right? Okay. So I'm definitely in the interval from 1 to infinity. There isn't any limit on how big I'm allowing the a to be, so we're good. Okay, so we started with an element in there and we ended up in there. Okay, here's where we have a little more work, is the other inclusion. So let's see, I want to show that if I have the interval from 1 to plus infinity, that's contained in this union. Okay. Same thing, pick an element in here, show that it's in there. So suppose we give ourselves an a that's in here. So we need to show that there exists an x so that that a is in one of these intervals. Okay. All right. So here's where I sort of do some scratch work. Okay. We want to find an x, maybe call it an x naught, so that a is in this interval. Okay. I think I'll just write x. So what do we need? That is, we need a to be greater than x squared, strictly greater, and less than x squared plus 1. Okay, so think of picking the a like 6, right? It looked like 6 was left out of the intervals that I had so far, but there should be some x I can pick that will cover 6. If I pick it close to the square root of 6, that should work. Let's look at this more carefully. So think of the a as what I know. Okay, we started with that. That's like my number 6. And I'm trying to solve for the x. Okay, so I can take a square root and find something about x, right? So we get, by taking the square root, x is less than the square root of a, right? And we'll also get this, which is a little harder to figure out, okay? But we at least know this much for sure. Okay, but this sort of says, all right, we don't want to take the x too much smaller than the square root of a in order to make that work. Okay. So what we'll do is we'll say, let's try x equal to something a little less than the square root of a. I have to make it less. So subtract something off that we'll call epsilon, because we think of epsilon as being a small number. Okay, and that will work. Then we certainly will get this that we want. We just now have to arrange to get this part. And we want to choose epsilon so that this works. Okay. This is still scratch work. Let's write it out. I'm using this for my x. All right. Got it? So I'll multiply it out. I have to do the square, right? So when I square it, I get this term squared. I get 2 times the middle term. And I get the last term squared. That becomes a plus. Epsilon squared plus 1. Okay? So this is what I need. Okay. And now we're trying to solve for the epsilon, or at least find an epsilon that works. Any epsilon that works should allow us to proceed with the proof. Okay. So let's check. Of course, I can cancel the a's, and then I'll put the negative term on the other side. And that's what we need. So let's see. The negative term I put on the other side. Just being careful to copy it right. Okay. And we're sort of trying to solve for the epsilon. Let me divide by this. I'm not exactly solving for the epsilon, but I am isolating the epsilon on one side. Like this. Okay. Right? Okay. All right. So let's see. Let's even write this out like this. Okay. Now, this is what I want to achieve. Okay, that's what I need. I don't exactly have to solve for the epsilon. There's more than one answer that will work. And notice that epsilon less than, I mean, this is complicating things for me. I want an answer that doesn't have an epsilon in it. I'm trying to solve for epsilon. Well, if I leave this out, so here's where I simplify life for myself. Notice that this will work. If epsilon is less than this term, then it will certainly be less than the sum of these two terms, right? So this is where the scratch work comes in. I didn't need to have an equality. I just need to have an inequality. It's easier to make this one. And then it says exactly, what I need to do for the epsilon. Okay? So this term makes it harder, but I can ignore it because I'm adding it on. That just makes it bigger. Everyone okay with that step? So that's the type of thing you do in your scratch work. And so let me say more specifically how I'm going to choose the epsilon. I want it to be less than that. So let me say I'm going to choose it to be specifically this. Okay. Because that will be less than that. Okay, make the denominator a little bigger. Good? Okay. Okay. I just realized that clock back there is way off. So we have just a few more minutes. Okay, so that was all scratch work. Then I'm supposed to proceed with my proof. Okay, we hope it's going to work. So let's see. So now finishing the proof. To proceed with the proof. Okay. I guess that's as far as I got with the proof. So assume that A is in this interval, right? And now I'm trying to show that A is in one of these. So I'm going to say take x equal to this, and I figured out what I was going to use for epsilon. Okay. Good. I think that'll do it. And now let's check. Then, first of all, part of the reason we did this was that x would be less than the square root of a, okay, because we subtracted off that. So x squared is less than a. All right. So far, so good. We're trying to show that the a is in this interval, so it's greater than the x squared. In the second part, we're going to try to get this. So let's see if it works. Also, let's write down the x squared plus 1 and see what it is. Okay. And what do we get? We get this squared. We get in the middle 2 terms which have the product of these two. Oh, we get some nice cancellation with the product of those two. That's sort of because of the way we picked it. Square root of a in the numerator, square root of a in the denominator, they cancel, and we just get 2 terms of 1/3. And then plus, when we square this, what do we get? 1/9 a, just a, right? Plus 1. Okay. How's that? Is that right? Okay, great. So let's see. This is supposed to be greater than 1. Let's keep going. The minus 2/3 and the plus 1. Great. Is it bigger than a? Yes, a plus a positive plus a positive. This is greater than a. Excellent. Okay, so my a did turn out to be less than this x squared plus 1, and it's in greater than x squared. So a is in this interval from x squared to x squared plus 1. So there exists an x with a in that interval, which means that a is in the union. That's exactly what it means. There exists one of these that a is in, so a is in it. So we've shown that every element in here is in there. That's our other inclusion to show that the sets are equal. All right, good. You get the idea of how to do scratch work.